Thank you. So I'll be talking about what I call hybrid MOND-dark matter models, and specifically relating to the recent weak lensing data that we've heard about this week as well. So let me start by quickly asking why hybrid models and what is the idea of hybrid models, what I mean by that. So when you think about cosmological scales and observations on cosmological scales, one thing you have to explain is the structure in the CMB. And famously, the simplest explanation we know of is to introduce some kind of collisions fluid, which gives this kind of oscillatory structure in the anisotropes of the CMB. On the other hand, if you think about galactic scales, one thing you have to explain is, well, there seems to be this very tight connection between the supposedly dark matter and the normal matter. So, for example, in the form of this radial acceleration relation. And the simplest explanation that we know for that is something like a modified force law or modified inertia. In any case, something that gives you a way to calculate the actual acceleration in terms of the baryonic acceleration. So an idea you might have is, can we have the best of both worlds? And I think that's the idea that is behind a number of models, although not always explicitly, and maybe it's debatable in some cases. But so all of the models I list here I view as a form of hybrid model. By that I mean that they have from cosmological scales some form of collisionless fluid, which allows these models to explain the CMB. And on the other hand, in galaxies, they have some kind of MOND force, which allows them to explain things like the radial acceleration relation. So in the example of neutrino hot dark matter, the role of the collisions fluid on cosmological scales is played by some form of neutrinos. And that's how you would explain the CMB in this model. The neutrinos can do the job, hopefully at least. And on the other hand, in galaxies, you don't have a lot of the neutrinos, still some, but they're hopefully negligible. And you do have a MOND force there, so that would be how you do the radial acceleration relation. So I think I categorize, as I said, all of these models up here in neutrino hot dark matter and dipole dark matter probably as well. Aether Scalar Tensor theory and superfluid dark matter are examples. I categorize all of them as hybrid models. Now, I'm not sure if Konstantinos would agree with me saying that there's a form of dark matter in these models, but I think that's a useful way to think about them. Personally, I've worked on these two models, but today we'll only have time to look in detail into the Aether Scalar Tensor theory. You can ask me about superfluid dark matter later. So that was one half of the ingredients. The other half is the weak lensing observations by Brau et al. That we have already heard about this week. So I will not be talking much about the data itself. So basically what we see here is the radial acceleration relation. Up here that's the kinematic data from the Spark database. Down here we have the new weak lensing result. And the basic takeaway is that it looks something like MOND all the way down to 10 to the minus 15 meters per second squared in baryonic acceleration. There's this shaded region where maybe the isolation criterion used for the analysis is a little bit less trustworthy. But in any way, this is pretty impressive, and it extends the known radial acceleration relation quite a bit. And so maybe this constrains some models, and this is what I will be talking about. So specifically, Aether Scalar Tensor theory is a model I've looked into, or we have looked into. I should say that this is not yet published. It's currently under review, so you might take what I say with a grain of salt. But anyway, here goes. So what we are going to do is we will solve the equations of motions in the so-called quasi-static limit. That is the limit of this model that is relevant to galaxies. What happens is that we have two equations, and the left-hand sides of these equations is pretty much standard for some form of equal type MOND theories, so nothing too weird going on there. The special ingredient, which is basically what all my talk will be about, is this term on the right-hand side, what I call rho c. So on the right-hand side, we have the source of the gravitational fields in this model. And rho b is the baryonic density, the standard thing we want to have in MOND models, because the baryons should dictate what happens, basically. But then there's this additional term. That is the ghost condensate density, at least in my view. Konstantinos calls it the mass term. But in any case, there is a term here, and I put it on the right-hand side. Konstantinos puts it on the left-hand side, but the mathematics is, of course, the same. So. I like to think of it as the density of this thing they have in a model that goes condensate. And it will have all kinds of interesting effects. So just to look at least very briefly at what is inside this condensate density, rho c. So first of all, we have a prefactor. That's just some model constant, just some number that you can choose. That is a fixed number. And then we have inside the brackets first the time derivative of one of the two fields we had, and then the absolute value of the sum of both of these fields. So that you have this kind of structure is a typical thing to happen in any type of condensate model, be it Aether Scalar Tensor theory, be it superfluid dark matter, or just a super standard superfluid helium or something like that. So I think the interpretation of this as a type of condensate density is pretty standard. What is an interesting technical point is that the gravitational potential appears here with the absolute value, which is a bit non-standard when you think about the theoretical structure of this theory having diffeomorphism, invariance, etc. So how can it be that the absolute value of the gravitational potential is physical? How can it be that it plays a role? And the answer is that it actually is just a combination of this phi dot with the absolute value that is physical. So it's not just the absolute value of the gravitational potential itself. And there's actually also a physical interpretation of what this integration constant that is now suddenly physical in this model is. Namely, it is the chemical potential of the condensate. So that is a physical way to think about what it means that the integration constant in your gravitational field that usually doesn't matter, at least not in the non-reducible limit, has a physical meaning here. So in any case, what this means in practice is that to solve the equations, you need not only the baryonic density as the standard in MOND, you also need to make a choice, choose a boundary condition, choose a chemical potential equivalent. Okay, so without further ado, let me show you what happens when you solve the equations. So this is again a plot of the radial acceleration relation. So x-axis is the Newtonian baryonic acceleration, y-axis is the actually observed acceleration, and I put here the absolute values, so the modulus, for a reason. What is shown as the diamond-shaped things is the kinematic raw, the observed raw, and the circles are the weak lensing raw that the new result by Brauer et al. So the slightly darker symbols here are where their isolation criterion is a bit more reliable, and the lighter circles are where you can be a bit more skeptical if you want to be so. But it's, it's something that's still measured. And I'm not an observer, so I can't tell you how much more skeptical you should be of this part of the data, but this is what it is. And now the colored lines are what let's say, our contribution is. So we solve the equations of motion of the Aether Scalar Tensor theory, and each of these lines is a different solution. Now the first thing to notice is that there's a structure here, a very strong dependence on baryonic mass. So each color here, so the green one and the yellowish one and the reddish one, they are all for different baryonic masses. So the first thing to notice is that there are these deviations from MOND that I will be talking about a bit more, but the first thing to notice is that the more massive galaxies, they start to deviate from MOND earlier than the less massive galaxies. So this is 10 to the 11.5 solar masses baryon mass, and this is just 10 to the 8.5 solar masses. And now within each of these colored lines, is these many lines of the same color. Each line is for a different choice of chemical potential, so different choice of boundary condition. So I do have a bit of a wiggle room of what actually happens. But there's also, like, whatever boundary condition you choose, there's a typical radius where you start to deviate from MOND. You cannot actually completely avoid this just by choosing very specific boundary conditions, something like that. Okay, good. So basically what I'm saying is that these kinds of oscillations that you start to see here, that's what they are if you plot them not with the absolute value, but without the absolute value, then there are oscillations, but I can't do that on the log plot, so I show the modulus. Is that they're not really reflected in the data. So can we do anything about that? And the answer is yes, we can do something about that. Because remember, there was this prefactor, which is a free model parameter. We can just make this model parameter small, then the effect of this condensate should go away. So we can just make this model parameter very small. Now, I have a very, very rough estimate of how small you have to choose it. It's not fancy statistics, it's just a very rough order of magnitude estimate. So if you trust the data to 10 to the minus 13 meters per second squared, so if you're more conservative, you should choose this combination of parameters smaller than 1 over megaparsec squared, roughly. If you trust the data all the way down to 10 to the minus 15 meters per second squared, you should choose this parameter 0.001 over megaparsec squared. So okay, fine, that's just something you can do. But you have to be careful for two reasons. The first reason is this. If you choose this very small value, what happens is that this condensate density, the typical value of that, is actually much smaller than the cosmological background density of your collisionless fluid in cosmology. So it's a bit weird, or it's not clear to me how you would embed such a low density galaxy in a cosmological background which has a much higher density. So that's one thing that's a bit weird about just making that parameter very small. But it's a complicated model, so I can't make a really strong statement about that, but it's definitely something I'm a bit worried about when I think about making this parameter very small. The second thing that I think will go wrong, but it's another hand-wavy thing, when you make this parameter m squared over t very small, is galaxy clusters. So one advantage these hybrid models have over MOND without the dark matter component on cosmological scales is that you can use the thing that is the collisionless fluid in cosmology to get a little bit more acceleration in clusters, which is what you need observationally. So there's this plot of cluster data shown in acceleration space that was already shown in this week already a few times. So you see that there's a bit more acceleration needed than what MOND provides, which is this dark line. So this is something you could potentially use the additional dark matter for in these hybrid models. But I think in this Aether Scalar Tensor theory specifically, if you make this parameter m squared OFT very small, this no longer works. But this is a hand-wavy, very rough estimate. I'm told that other people are working on clusters in this model, and soon we should know more precisely what happens at cluster scales in this model. There are a few caveats. The first one is these oscillations correspond to negative densities of this, what I think is a condensate density. And physically, you might expect that these negative densities are actually unstable, so they probably don't exist in nature in equilibrium solutions. So, but I don't have proof that. It's just an expectation. I haven't done the calculation. So you might think, well, let's cut off the solutions where the density turns negative, and what you get then is this. So all the solutions, they go up, but then they stop. But no one really knows how to continue them, so I can't tell you really. So if they're unstable, that is, then I don't know what happens then. That's an open problem. Maybe maybe the condensate is no longer condensate, but is whatever makes up the condensate. Like a superfluid helium might no longer be a macroscopically coherent condensate by the individual atoms or something like that. No clue, that's just speculation. But that's one of the caveats. Another is that the weak lensing data is not for individual galaxies, it's for a huge number of stacked galaxies. That means, in some sense, averaged. So what can in principle happen is that you can hide a lot of deviation from MOND in this stacking, averaging process, in principle. So for example, here I show you the green lines, solutions for each solution has a different boundary condition. And if you average them, or all of the individual green solutions deviate from MOND quite a bit. But if you stack them, if you average them, they land on the MOND expectation pretty closely. So that is one thing that can happen, in principle. Of course, you need special boundary conditions for that, and it's probably not very likely that you do get these special boundary conditions. To know, you would have to do nonlinear structure formation simulations in this model, which we don't have yet. But so that's another caveat to keep in mind. So that's what I wanted to say about this specific model. Now let me try to make a more general point about these kind of hybrid models in general. Namely, I think that probably any hybrid model has similar problems in reproducing the weak lensing data, given that we want to embed all these models in a cosmology that has cold dark matter-like behavior. And the argument goes like this. So all these hybrid models, more or less by definition, what I mean by hybrid model, want to have a cold dark matter-like cosmology, so some form of collision is fluid on cosmological scales. What that means is that on cosmological scales, you need some form of dark matter with a density of order the critical density. Maybe it's 0.25 critical density, but it's just a rough estimate on the order of the critical density of the universe. Now, if you have this physical picture of galaxies being the result of perturbations, overdensities growing a bit, then galaxies are overdensities, also probably in overdensities in this thing that is a collision fluid in cosmologies. So in galaxies then, which are the result of this production of overdensities, you have a lower bound on the dark matter density in galaxies on the order of the critical density. Just a rough order of magnitude estimate. Now you can convert that lower bound on density in a lower bound in mass just by multiplying the critical density by the volume of the volume we're interested in. So let's say we are interested in the Weak lensing data. The Weak lensing data extends all the way to megaparsecs. So let's just multiply this number here, the critical density, by the volume of a sphere with 1 megaparsec radius. And what you get is 6 times 10 to the 11 solar masses. So roughly you would expect that in any of these hybrid models, within a megaparsec, you have a dark matter mass of at least 6 times 10 to the 11 solar masses, which is larger than the baryonic mass of most galaxies. So I think that's a problem, because usually I think what this means is that all these hybrid models probably, this is not a hard proof, okay, it's just a hand-wavy order of magnitude estimate, but these hybrid models probably all deviate from MOND at megaparsec scales. And this is not what the Weak lensing observations show, at least if you believe also the part of the observations that are in this, where the isolation criterion is maybe not as reliable, where this is shown in the shaded region in their plots. So that's a kind of argument that I guess some theorists will try to find a way around, including me. So let's see what happens. But I think that is a challenge for all these hybrid models. And that's what I want to say. Thank you.
So one conceptually I want to clarify is that these lensing. So one thing I wanted to clarify conceptually is that these lensing observations are sensitive to the overdensity, or the excess of the mass above the cosmic mean. So it's fine if you postulate that the overdensity is much smaller than the background, because that just means the fractional overdensity is very small. So it's still physically meaningful to have a galaxy with a density much lower than the cosmic mean, because here we're just talking about the overdensity. That's what causes the...
So I think I kind of assumed that.
That's kind of implicitly assumed. Okay. So what I really wanted to mention though is if you show the weak lensing area, then the Brouwer results. Yes. So when you're saying that you're not allowed to add extra mass at the low mass end, low acceleration end, I mean, there could be a cancellation between the effect of the EFE and the extra 600 billion solar mass figure that you estimated.
That's true.
So that's something to bear in mind.
And I think that can happen, but also keep in mind that Brouwer also have plots of various cuts. So they have a plot like this where they split the sample in different masses, and also where they split it in early and late types, and you always see more or less the same thing. So you would have to make the external field effect and this cancellation work in all these cuts and not just in this one plot.
It have to be a little fine-tuned.
Yeah, which I think is rather unlikely, but you can probably still have it.
So, and just one very quick question. Can you go to slide 8? So you kept saying that the absolute value of the potential came in, but there aren't absolute value signs on here.
Okay, what I mean is the value of the potential without derivatives.
Oh, you mean, but you don't mean that. Oh, I see.
Yeah, okay.
Right, okay, I see.
Right.
Okay.
I am not sure if you included in your hybrid model the previous model, multipolar dark matter, but actually the general argument that you give does not apply to this model, because in this model, the cosmological density of dark matter does not grow like the baryonic dark matter, and so it is smaller than the baryons in the galaxy after cosmological evolution.
That's good. So does it not grow at all, or so is the galaxy not in overdensity at all in this?
We conjecture that it stays close to the cosmological value, but we checked by.
Because I think even if you have like just overdensity just of a factor 1 or something, it could be a problem, right?
Yeah.
In the same vein, why doesn't your final argument argue against dark matter? Because there are dark matter models that seem to.
I think the idea is this.
It's the same there, isn't it? Dark matter.
So the 6 times 10 to the 11 solar masses in a dark matter model is not necessarily a problem for dark matter models, because they don't, or what I want to say is this, in these hybrid models you have the MOND forcing galaxies. So that's what, with just the baryons plus the MOND force pushes you to this data model. And if you then also add as a source another mass, that's what is a problem, if you enhance it by the MOND new factor. Of course, if you don't have the MOND enhancement with the MOND force, then this dark matter mass in itself is not a problem.
But you do have the MOND.
Yeah.
A lot of dark matter in the galaxy itself.
Right.
Maybe Tobias.
Just,
I was wondering why you don't.
Oh, well, you has much urgent question, more interesting. I just have a boring question. If you show the equation on the where you show the fact, just quickly, term Fg is one of these
Yes.
combinations of K's and stuff constant, so it's not really varying, right? It's
It's a number.
It's just a number, so it's better if you absorb it somewhere. The definition.
I mean,
it's confusing for people to see another thing. Okay, but and also I noticed the total acceleration in the power in that plot goes to 0.
Yes.
Why is that? Can you say why that is?
So at some point the density turns negative. That's at this point at the top, where the bell bump is at the top. But then the negative density integrates up, so that the mass is 0. That's where the acceleration then is 0.
So there will always be such a point where a total will be 0. Is that what we call virial radius for the 200 times the background density?
I don't think it's related.
Oh, but then where is this radius for the Milky Way?
Few hundred kiloparsecs, depending on the value of the model parameter m squared over fg.
Okay, anyway, it's in that ballpark of virial radius.
I mean, yes, but depends on the value of the
Maybe
model
turn
parameter.
around the radius or something.
Sorry?
Maybe there are different radii. Maybe there's a radii for the turnaround radii in standard cosmology. Okay, I don't want to take up extra time from us.
Okay, so our next speaker is indeed Françoise.